Good afternoon, everybody. We have the GPS visualization and validation tool. Our client was enabled to receive warfare in Newport, Rhode Island, as well as the command. Today, I'm joined by team leader Melanie, Thibodeau, Scrum Master Tim Lahiff, developer Isaac Lacombe, and myself, Nathan Brown. Moving on, so what exactly does our project encapsulate? We had to develop a tool, Data to Linux, that utilizes data pulled from the United States Navigation Center website in the UMass and SEM file format, perform calculations such as Kepler's law of planetary motion, determine the satellite location, and chart those out on a Skyplot. As you can see on the right side of the screen, we have a newly provided Skyplot. You can see the different colored tails. Each of those indicates a different satellite location. We just use that as a reference for our own. Moving on, we had a couple different project requirements. Again, importing one or more of those GPS Almanac data located on that Navigation Center website. We'll be getting into the data a little bit after this. We had to calculate the GPS positioning using values retrieved from the Almanac files, perform those calculations, like the Kepler's law of planetary motion, and to produce one of those Skyplots we showed on the previous slide. We had a couple additional features that we implemented, namely a user interface, so the user can directly interact with the backend of the program and get whatever information they want to pull from it. A visual representation with a calculation of the satellite information. Again, just ease of use so the user can see exactly what type of information they're looking for. A specific field pull that we can see if we want to pull all the information pertaining to the health of the satellites, all 1 through 32 of them. We can do that in the program. And a help section to help guide a user through the program if they're unfamiliar with the structure. So just to get a little bit into our program structure, we broke it down into 4 main components. The front end, again, so that user can directly interact with the program. The midwall, which we use as a device to pass data between the front end and back end. The back end handled all the information from importing the files, breaking down the data, and actually manipulating and doing the equations provided. And the Skyplot, which takes elements of all 3 of those main programs that I run through. It takes the user request from the front end, pushes it through the midwall, which then requests specific files from the back end. Once the calculations are done, they're pushed to the Skyplot function and pushed back to the front end for the user to see. So before we get into the front end and the graphical user interface, I'll cover the data set first. So, like I mentioned before, a lot of the data they implement is from the United States Navigation Center website, imported in the UMass and SEM file format. We provided visuals on the right side of the screen. You can see that the data looks pretty different from each other, but I can assure you that the information contained within those 2 files pretty much the exact same. The main difference between them is kind of the readability of the files. The UMO file, you can see, is broken up into keys and values. You can read it pretty easily, pull whatever information you want from it just visually. The SEM file format's a little more difficult. There's no labels on the information that you're looking at. And then getting into the actual way we broke down the data. First and foremost, we pulled the data into the program, initially with a requests library, so we can take a hyperlink from the United States Navigation Center website, for example, and pull it right into our workspace. We did later implement a function, so if you do have one of those files saved on your computer already, you can just drop that right into the program. Then after that, we did reformat the files. So I just provided an example of the UMA file, the one that's easily read beforehand. You can see on the right side, it looks a little bit different. We did trim out some of the initial data. You can see the headers for each individual satellite was completely trimmed out, mostly because they provide unnecessary characters, and the information in those headers are already contained in the data set below it. So we trimmed those out, and we did get rid of the spacing in between the keys and values. This was important later for when we convert them to dictionaries and then JSON files. I'll begin with that actually right now. So this is one of the most important parts of the project. It helps make the data easily pulled in. I know the visual is a little bit hard to see, but the main gist of that visual is just to kind of show how the data is broken down. You can see the blue and the red text pretty clearly. It's a little difficult to read what they actually mean, but the blue text is the keys that I was showing earlier in the UMass and SEM file format. Those indicators that tell you what those variables are, and the red is the values that pertain right to it. So the reason why we broke this down into this kind of structure is pretty simple and straightforward. It helps the actual coding process for these calculations a lot easier. The way that it works is there's 2 different dictionaries that we utilize that we convert into the JSON file. One of them you can pull directly from the satellite. So if you want to pull the information from satellite 5, you just specify that satellite. The next dictionary set is the actual variable you're looking for. Say if I want to find the eccentricity of the satellites, for example, I can do that right away. And then here are some of the actual equations and variables that we used. I'm not going to get too in depth into them when you guys fall asleep on me. But some of them were really hard for us to kind of figure out on our own. It's not exactly a field that we're super familiar with. So I'd like to extend a thank you to the Melanie and the physics department at the UMass Dartmouth University for helping to clarify those variables for us. But I just wanted to show off a general structure for one of our equations. We broke them off into branching equations, mostly for readability for somebody else coming into the program. It also helped us kind of maintain a very clear structure in what we were actually developing. We broke it down into several components instead of having it all contained in one section, mostly so in case we did need to recall another variable from a different section of the program, we could absolutely do that. We just pass the variable into the next equation and we can pull it right from there. Again, I just wanted to kind of hit upon that point. This was a very, very common structure, so although the actual development of the formulas looks different, the general structure still remains the same. I provided just two example equations right there for the latitude and the x, y, and z coordinates of these satellites, just to kind of hit upon that point. So getting into a little bit about the actual formulas themselves, we can find the x, y, z coordinates of each satellite individually by implementing those equations and the variables we had shown before. A lot of these are already stored on the actual GPS almanacs themselves, but a lot of them we also did have to do some equations for. But once we find the x, y, and z coordinates of each individual satellite, we can push those into latitude and longitude coordinates, and then we can help narrow down exactly where it is over the Earth the satellite is located over. And then I just want to hit upon two different calculations that we did. So the first one is distance, so pretty much the exact distance from the actual satellite itself to the user in nautical miles. It was pretty simple to actually implement this. We had to find two different latitude and longitude pairs. That first pair we already found before. It was the satellite location that was the calculations for. The second pair is the actual user's location pertinent to their actual location. So we just found the difference between these two pairs of latitude and longitude points, and we can put that right into nautical miles. The second was the azimuth, which is the angle at which the satellite is located to the user. Pretty much the same exact structure. You can find the latitude and longitude of both the satellite and the user, and kind of extrapolate the azimuth from there. For example, say true north is directly in front of me, and the satellite is directly east of me, say if it was Isaac or Mel, it would be 90 degrees relative to my location. It's that, the difference between true north and the tilt to where the satellite is actually located. And with that, I'm going to be passing this off to Tim to go over the midwall and the front end of the program.
Thank you, Nate. So first off, I'm going to talk a little bit about our midwall. So it's pretty much our connection between the front end and the back end of the system. So all of the values that we're going to be passing for the calculations and importing the data, that's all going to be handled by our midwall. And now onto the front end. This big picture we have right here is our GUI. So that's going to be the main screen that you're looking at when you open our program. We separated it into three sections. We have our upload file section, our search file, and our display file section. In our upload file section, we have the ability to upload either the UMA or SEM files that Nate talked about. And we can do that using our URL that you can copy and paste in there, or you can search your file explorer and load it up that way. Once the file is loaded into our system, you just confirm that that's the file that you're looking for. And you can also use that View All Imports button, and it will deploy a separate window, like the smaller one here, and it'll show all the files that you've loaded into our system. And so once you choose the file that you want, you can go ahead and search for the specific GPS in that file. So each one of these files contains 32 GPSs, so you're going to be searching 01 to 32. And once you've done that, you can go ahead and search the specific fields that are in each GPS. So if I want the health for every single GPS in one file, I can just search health down into that bottom text bar, and it'll bring up a window with that. And then in the display file section, we have 4 buttons, one for calculations, which will display all the calculations that we ran for that one single GPS. Graph one satellite, which will show one satellite at one point in time. Graph satellite over time, which will again show one satellite, but over a period of time, so it will show the trail that the satellite moved along. And then we have a help button that shows or answers any questions you have about our GUI. So these are the different windows that deploy from our main GUI window. The tall one over there is our calculations window that deploys when you hit the execute calculations button. We have an error window that pops up if you do anything that's not allowed in the GUI. Instead of crashing, that will deploy and prompt you to try the action again. The one down the bottom here is the field, so it looks like we grab the health for GPS 1, 3, 4, and 6, also 8, and they're all reading up as 000, which means that the satellite is healthy. And this is the health window that I talked about earlier. We split it up into two separate because it was too long on the screen. And so this is our Skyplot. As you can see, it's very similar to the one that you had provided with us. We were aiming for that because nobody in our group had any experience in making Skyplots before. So we used the Python libraries AstroPy and AstroPlan to aid us in making those. And the satellite is depicted by that little O up in the top left of the screen. And this is Skyplot blown up. This is if you hit the one instance of the satellite, it's showing one satellite at one point in time. And this is one satellite over a period of time. You can see the trail that the satellite is moving upon. And so for our project tools, for all of our development, we coded everything using VS Code through Anaconda. All of our code was stored in the Bitbucket repository, so anybody on the team could access it at any time. Like I just talked about with the Skyplots, we used AstroPy and AstroPlan, and per request of our client, we coded in a Linux environment all using Python. And the team communicated all over Discord and Slack. We communicated with the client using email and iMessage, and all of our client meetings were conducted over Zoom because our client was offsite. And as far as the planning of the project went, we planned everything in Jira, so all of our tasks, our sprints, and our stories were all stored in there. All of our meeting notes, so Scrum meeting notes, client meeting notes, all of that was stored in Confluence, and all of our documentation was done in Google Drive. And now Mel's going to help me present the demo. All right, so first of all, we are going to try to bring up an error message. So we're going to type a random string in there and just search it up, and we get an error message. And then we're going to go ahead and load an actual file into our GUI. And we get no error message there. We open the file, so it's working. We hit view all imports to show that it is indeed in the system. And we move down to the search file section, and we can, once again, just choose that file, make sure that it's all selected and ready to be searched through. All right, and then we're going to search the specific GPS that we want to look up. And once again, we're getting no error messages, so we're all good. And let's go ahead and search the health of GPS 05. And as you can see right there, it pops up just the health for 05 is 000. So let's try and execute the calculations for that. And once we hit that execute calculations button, the time window is going to pop up, and that will show, so each file has a period of time associated with it, so we're just going to search today's date, and 000, which will just be the very beginning of the file, and we're going to search that, and it will deploy our calculations window for GPS 05. And then we can go ahead and try to graph one satellite, and you'll see the same time window pop up, so we're going to search the same time period. And there's the GPS plotted out on the Skyplot there. And if we just go and hit the help button, that will include our demo, and that's all the information you'll need for the entire movie. And so that concludes our project. Does anybody have any questions?